Yeah. Last time we were looking at some special subsets in R2. So looking at, and the special is connected subsets, looking at connected subsets in R2. Obviously, this word connected is intuitive to us, but we had to define it in a formal way so that we could, mix it with other concepts of analysis and so on. Why are we interested in connected sets? Yes, exactly. Yeah, I'll come to that. That's right. Yeah, I'll just come to that after this. Yeah. So the point is that I just want to share that connected set. We are studying connected sets in R2 or in C, but that's the same thing because we are only using the geometric properties, and that's the same. Geometric, I mean just the distance properties and so on. They are the same. So the subsets we are studying connected subsets, and that's because later on when we study functions from subsets of C to subsets of C, the subsets on which we will be studying the functions will be connected because we will want to do integration on the subset and so on. Just like when we want to do integration in our the real line, we take intervals because we have to partition it and so on. It has to be a connected thing. So in this case also, we want to do our work on connected sets. And so we defined connected sets and so on. So you understand that. It's just that something that cannot be broken up into two pieces, and pieces here means two open pieces. Okay, and we gave some other definitions and so on. Yes, so let's come to the question that we had last time. So we were trying to study, I can put it as behavior of connectedness, because now that we've introduced the concept, we would want to study its behavior under the set theoretic operations, union, intersection, and so on. So behavior of this will help us to understand this, in turn understand the concept better. Connected sets under set theoretic operations, union, section. So can you tell the exact question that we were doing? Yes, so we have proved that R2 is connected, but under this subtopic of unions and intersections. So here we were looking at this, right? Let C1 and C2 be two connected sets in R2, of course. Then is C1 intersection, sorry, C1 intersection C2 we saw is not connected. That is very easy to see. But is C1 union C2 connected? Yeah, this. Do you mean path connected? Path connected, yeah. So we saw the concept of path connected. That is basically a set in which from any point to another point, we can draw a path, basically image of a continuous function. Yeah, and path connected sets are obviously connected. For that, we have to prove something, but yeah, but let's first do this one. This has not much to do with path connectedness. Just to do this problem though, we are asking this because of some question in path connectedness, but we'll come to that later. But just let's think about this itself without path connectedness, just connectedness. So connected basically here, we mean that you cannot write it as union of two, disjoint, non-empty open sets. Yeah, let's think about this. Yes. Not disjoint meaning? Why is it not disjoint? There might be, right? There might be. Then what can you say? Okay, so let me write your claim in a more formal way. Empty. Okay, are you sure about this? Let's think about this. No, C1 may not be disjoint. C1 may not be open. Right? C1 may not be open. That is the thing. Yeah, think about that. C1 may not be open. So yes, so C1 and C2 may not be open. If they are open, then certainly what you're saying is correct. For example, if I take C1 as a circle, as a, let me just draw it. If we take the situation like this, centered here, if you just take a ball, interior of this, and then we take a ball here, so suppose this is always the origin, and this radius is 1, and this is 2 comma 0, and this radius is also 1, and these are open, meaning that we're only taking the interiors. We're not taking the boundary in the sense that we're not taking where the point where the radius is 1, that boundary that we can define. We're not taking that. Then you see these two are open, right? So these two are open balls, so they're open and they're disjoint. And so C1 union C2, then in that case is a union of two open disjoint things. So it's not connected. But where is the problem? The problem is that this is just one example, right? C1 and C2 need not be open, right? Maybe I should say need not be open, right? So in those cases, it is not connected. You're right. Yes, right. So we'll say that, but here I'll say that if C1, C2 is open, right? At least this we can say with surety. Right? So, but I'll exactly, it's not universally true, right? That's right. That's right. So I mean, what you're saying, so basically if you say no, so if your answer, if you just say that the answer is no, you're right, because this statement is not correct. Right? For it to be correct, it has to be always correct, always, also, right? And so you are right. I mean, you have given an example, or you have taken a case where they are open and the intersection is empty, and you're saying it's not connected because you're able to write it as a disjointed. The answer is no. Perfect. So you're right. But your reasoning is not right, because C1, C2 may not be open. So let me come to that. So what I'm asking for you, and then I'll give the example. First, you can think. If, okay, give an example, but my point is that it is not universally false also. Give an example such that C1 intersection C2. What is universally false? This statement? Sorry, can you say that clearly, fully? Oh, that is different. No, that is not universally false. There can be two kinds of things, right? Sometimes it's true, sometimes it's false, that you can see, but then that means it is false. I mean, as a statement, obviously, but it's not universal, it's not always false. Again, that you can take some examples. Just take two intervals. This intersection is also an interval and it is connected. So yeah. But here I'm asking this so that we can understand this concept better. Given examples such as C1 intersection C2 is phi, but C1 union C2 is connected. Think about this an example. So two sets which are connected, obviously. Their intersection is empty, but still the union is connected. See, if you have a set which is connected, it does not have to be open. Just take a closed interval, right? Right? That is not open. It is not open because by the definition, right? If you are at 1, then you cannot draw balls which is inside. Any ball you draw, obviously this is not open, we know that. You can take a rectangle in R2, you can take a star, you can take a ball with a boundary. Or maybe this can be, I'm also just thinking about this. Yes, yes. So I may be wrong. Yeah, I was thinking about it for some reason, but I think it is, yeah. So that's right. Your intuition, I think, is correct. It cannot be possible. The reason I was thinking was, but you just give me 1 second. You're right. Yeah, it cannot happen. 1 minute. 1 minute. But you see, there are some limit points, right? I mean, the two things. Getting a little stuck here. So what I'm saying is that if it is a closed circle like this, it's a closed thing, closed circle, and then you take a open circle. Yeah. So obviously, but I was wrong. Obviously, this is also disconnected. Okay. This is also disconnected because, but you see the point, what I was trying to make is that, so what I was trying to make is that if you take any open neighborhood around this, what I was thinking, but that is not correct. If you take an open neighborhood around this, it will always intersect this other thing, right? You take any open ball surrounding this thing, right? It will always intersect the other ball. So you cannot write it as a union of two open sets in that sense, right? So you cannot write C1 union C2 as a union of two open sets. That is what I was thinking, okay? Because, so I can also try to convince you like this, though it is not correct. You see, that if you draw any ball which contains the first set, right, it always overlaps a little bit with the second set. Okay, so you cannot write, so that kind of maybe suggests that you cannot write this as a union of two disjoint. You cannot write this union as a union of two disjoint open sets. Okay, But that is wrong for the following reason. Because see, C2, so this is my C2 and this is my C1. Okay. C2 is open in C1 union C2, right? Because C2 is open in the whole space. Is that right? Yeah. C2 is open in the whole space. Okay. So C2 is open in C1 union C2. But C1 then is not open, right? But C2 is also, this is a claim, is also closed in C1 union C2. And this is probably a concept that I've not explained earlier. So let me explain this through a simpler concept first. Okay. I have not clearly explained this about something being open in something and the not being open as something. Okay. So let me just explain that a little bit, then I'll come to this. Okay. Yeah. So let us take an example. If you take a closed interval, this is closed, right? This is closed because what was the definition of closed? What definition of closed do you know? What definition of closed do you use? That, so we can use one definition that it has all its limit points, right? 0, 1 has all its limit points. You can use this definition for the time being. Okay, what does it mean? It means that any sequence which is inside its limit, if it has a limit, the limit will also be inside. Yeah. What this means, and this is an important thing to understand, is that if x is outside, if x is not in, yeah, if x is not in closed 0, 1, then x is not a limit of any sequence in 0, 1, right? That's just the same statement, right? Then x is not the limit of any sequence in 0, 1. But so you understand these things, right? These two things are the same. Okay. X has all its limit points, means that all possible limits that you can get out of all possible sequences is inside 0, 1 only. So obviously anything outside cannot be the limit of any sequence which is inside. But this also means that, see, if you, and you can just see it very clearly geometrically also, but we need still the definition, that if you take any point outside, well, you can take that point in R2 also, any point like this, then you can make a neighborhood which is completely disjoint from 0, 1, right? Any point outside, you can make a neighborhood which is completely disjoint from 0, 1. And that is because x is not the limit of any sequence, right? Because x is not the limit of any sequence, you can make a neighborhood which is completely disjoint from the set. Because if you make neighborhoods and they all keep intersecting, then there is a sequence which is converging to x, right? So this means that there exists a ball B. It can be a very, very small ball, but there will be a ball B around X such that B intersection 0, 1 is empty. So you see, these are all the same things. Okay. Now you can replace this by any set S. in R2. S is closed, means S has all its limit points. Or if any point is not in S, then it's not the limit of any sequence in S. Or that is the same as if any point is not in, which X is not in S, then there is a ball around B which has nothing to do with S. Okay. In this case, we will say that S is closed in R2. This ball will be in R2. Okay. Now, if this is clear, let's come to, yes, let's just go to a new page. Yeah, second page. Let me give you a different example. That was just a normal case, right? The space was not changing. But let's look at this. Let me ask the question. Is this closed in R? Think this. Yes. So you can use the definitions on page 1 and you can think about this. Take a time to think about this question because, yeah. Yeah, hi Rishabh. Oh, okay, okay. You didn't see it in the daytime. Yeah, yeah, okay, okay. Okay, okay, okay. Okay, ठीक है. You okay, okay. I'll just review the things. Yeah, actually, the class timing was not fixed. That is the other problem. Yes, yes, yes. Okay, okay, no problem. So, have you seen the last classes thing? Did you get a chance to see that? Okay, okay, okay. That is fine. Okay, so but currently we are doing this. Currently, I'm asking the following. Let's just keep this and ask this: Is 0, 1 like this half open and open on one side? Is this closed in R? Because again, we are realizing that we need to just take a closer look at this closed open side or closed and open notions. So is this going to be closed in R? That's right. Yeah. So your answer is no. Okay. Yeah. Rishabh, what definition of close do you know? Because there are several definitions. So if you know any definition, you can say, then you can answer in terms of that. Yeah, closed. What is a closed set? When do you call a set closed? Yes, 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 yeah. So do you use that definition or some other? You can say. Okay, okay. So, but let me just quickly review this. So, see, the definition we are using right now, basically, we want to call something closed. See, when do we say closed? Closed means that when you do some important operation and the answer does not go outside, right? So in general, what does closed mean? So this also applies to closed operations, closed operator, closed whatnot, right? So closed means always that in the context of some operation, in the context of something you do, and it's important to understand this in the generalities because when you see this in several places, closed sets, upper closed sets in posets, or closed sets here, or closed operations in algebra. The word closed is used throughout mathematics, but they all basically usually used in the same sense. Closed in context of some operation. What is the operation in analysis, right? In analysis, the operation is limits of sequences. These are the interesting things for us. Yeah. So closed set means that it should be closed under the operation of limits of sequences, right? So S is, so you can just form your own definition from here. S is closed in, now that is important. In what? Okay, that is also important. But here, let's say S is closed in R2, but in connectedness, something more is needed. That's why we are visiting this concept, relative closeness. S is closed in R2, okay, means any limit, any sequence in S, if it has a limit in R2, that limit is NS. Okay, so it is closed under the operation of taking limits. Okay, S has all its limit points. Pictorially, obviously means that X has its boundary, right? X has a boundary and so. But this is by itself maybe is not too very useful. You have to see this in slightly different ways. So can anybody say a slightly different way to say the same thing? This is okay. S has all its limit points. Can we say this in terms of points outside S? So it means that, well, just a restatement is that if X is not in S, then X is not the limit of any sequence in S. This is also pretty the same thing, right? But this means that, I'm not writing this, that if X is outside, then there is a ball around X which does not intersect S. Okay, something like this. Close means has its boundary, has a clear, thick, clear boundary. Okay? Which means that if there is a point outside, if some point is outside, then it is outside. Means that it is topologically or analytically outside, which means you can draw a ball, you can do your calculus on the point X around the point X without having to do anything with S. You can define derivatives and everything for that point without needing anything from S. There is a ball which is completely outside. Okay. So this is almost a repetition of what I said before Rishabh joined. But I've just added this new thing here so that when you see this concept in other places, you can. But let me, since I'm saying this thing second time, the other question that I can ask is, What do you guys think? Will it matter if I change the bigger space or the parent mother space? Will it matter if I change the bigger space? Let's look at the definition and think. Will the definition change or not? So for example, if I change this from R2 to something else, then can a set become which was closed in R2, but then if I change the space, then it is not closed anymore? Can that kind of thing happen? Uh, why is that? I mean, no. I mean, what you're saying is certainly correct, but the reason is a little more different. Okay, but okay. So let me not go into that abstract thing. No. Let's answer that through this question only, through this question that I've asked. So I suppose this is clear to everyone that this is not closed. Now your question will be answered once I change this. Okay, so this is okay. It is not closed. Okay, to both of it, because obviously one is a limit and one is not in the set. Cool. Now here is a changed question. But yeah, Raghav, what you said, if S is closed in R, then it is closed in R2, it is correct. As a statement, it is correct. But the reason is not correct. And a lot of times it's not true. Like if something is closed in something, then it's not necessarily closed in the bigger thing. Because in a bigger thing, you'll have more conditions. And let me not just say that in the air. Let's actually do it with examples. And here is the question. Is 0, 1 closed in? So now I'll replace this by X. Okay. Closed in minus infinity to 1. Because for connectedness, we need this concept because it's a very important thing. But in this case, we don't have R. The question is only this. Why not? Is 0, 1 not a part of this? I mean, it's obviously contained. Maybe. So 1 is not there in any one of them. So that's not a problem. Which one? Minus infinity to 1. Oh, yes. That is, oh, yeah, that's certainly round bracket. Otherwise, the question will not make sense. It's round. That's right. Obviously, that's round. Otherwise, where X is the limit of any sequence. Yeah. Yes. So let's write that. So there is no point. Let's write that in words only. There's no point outside 0, 1 in the space that we are in our present universe, in this, which is a limit of a set of a, you can say set also, but of a sequence in this, is inside this. Absolutely. Yeah. The only other thing that would have been there was 1, but 1 is not even there. Yeah. So 1 is not a limit of any sequence in the mother space. So there's no question about it. Right. And so just to put it very cleanly, you can just say that any point outside, you can just make a neighborhood which just has nothing to do with 0. Okay. So yes, you see, so the that's what I was saying, that this answer can change depending on your space. Okay. Now, obviously, there are precise ways to say this, but let's only develop what what naturally evolves. So let's not put some 5, 6 definitions and then something is closed or not will depend on closed in what. Okay, and similarly, open in what. So is this okay? All right. Okay. Now let's come back to this page. Okay. Let's take a second. So if you see books like Rudin, Barton Shabbat should all, I don't know if he deals with this thing, but Rudin certainly does. Many more elementary books will also do. Goldstein will do, but they might not. I mean, they'll introduce a definition, relative closed, and so on. So yeah, so that may become a little abstract. But once you see this, then when you see that later, you can just relate to it easily. Okay, so now let's come to this question. Give an example. Now this, I realize that there's no example, I think maybe, but yeah, but certainly what I was thinking was wrong. The question is, give an example of sets C1 and C2 such that C1 is open. No. Okay, the question is gone, right? So let me just, let's do one thing. Let's remove this so that there's no confusion. Yeah, now I think it will be clear. So C1 and C2 are two sets and they need not be open, but they are connected. Okay, C1 and C2 connected. Give an example such that C1 intersection C2 is phi, but C1 union C2 is also connected, even though the intersection is phi. So this looks wrong. Okay. Here is an example which I was trying to make. So let me just say this, what I mean by this. C1, so what I made is, so what I was thinking is that this is possible. I was thinking that this is possible because if you take C1, right, and you take a closed ball, and then you take open ball, so this means it has the interior but does not have the boundary. Yeah. Certainly these two sets are disjoint. They would have touched each other, but since this is open, it doesn't have the boundary, so they don't touch. So these are disjoint sets. I was thinking this is open, but this is connected, but it is not connected because C2 is closed, right? C2 is closed in C1 union C2. Can anybody give a reason why C2 is closed in C1 union C2? Now that we have explained this a little bit more, the statement. C2 is open is clear. C2 is open. But why is C2, this open ball, why is it closed in C1 union C2? Anyone can explain that? Just like the interval that we took last became closed when we changed the mother space. Here also the mother space is not R2, but C1 union C2, right? And so it is closed, right? Because you see, I just simple, right? Take a point which is not in C2. So take X, which is not in C2. This is not an efficient way to do it. There is a better definition of something being closed in a smaller space and so on. But I'm just trying to do this from the basics without any technology right now. So let X not be in C2, but okay, let X not be in C2, but in C1, but X in C1. I mean, that's what it means, right? That X is in the union, that we have to take something in the union because we're talking about being close in the union. So the union is our world, and we're taking a point X which is not in C2. When you take a point X which is not in C2, it is in C1. Now, obviously, if a point is in C1, can you, oh, Sorry. So this is the wrong definition. Sorry. Sorry. Yeah, let me just put it like this. Uh, sorry. I'm also learning. Sorry. So is C2 closed? Sorry, in C1 union C2. Let's just now you guys think about this, please, according to the definitions we have given. So does it have all its limit points? Or is there any point outside which is a limit point? Is there a point outside C2 in C1 union C2 which is the limit of something in C2? Okay, what about 1 comma 0? So this is C1 is a ball of centered at 0 with radius 1 unit ball. Yeah, but that is there, right? So that is a problem, right? 1 comma 0 is not in C2. Is that right? 1 comma 0 is not in C2. That's theoretically right, clear. But it is a limit point. That is, just try to make a ball, you will end up in C2 a little bit, right? But yes, I mean, that's very clear, right? Just make any ball. Again, this is not a very precise thing I'm saying, but just try to take this point and you make a ball. To say it precisely, I have to say that take a ball in R2, then take its intersection with this set. That is the definition of a ball in this. So I'm not defined what a ball means in the smaller space, but you can understand, right? Just take a ball and take its intersection with this piece, with this smaller space, right? So if you take a ball, this yellowish thing that I've drawn, right? You look at it, just the C, right? It's obviously intersecting C2. It is a limit point, right? And obviously you can just take a sequence that tends to 0 comma to 1 comma 0, which is inside C2, right? So, but 1 comma 0 is a limit point. 1 comma 0 is a limit point of a sequence in C2. And you can obviously create a sequence. I mean, you can just create a sequence. You can just take 1 plus 1 by n comma 0. That you see that sequence is in C2. So that's just, so even without all this, ball and so on and whatnot, you can just give this simple way if you want to convince yourself. This is the way you'll be building, because see, in one day, all the 10 different definitions or formulations will not be clear. So you have to fall back and forth from one definition to the other. You'll be comfortable with one of them more, and you use that to get comfortable with the other. And slowly, hopefully, I mean, I am getting comfortable with these things. Okay. I mean, to whatever extent I'm trying. Okay. So yeah, this is the thing. So you see, it's not. And so it is not closed. So then it means what I was initially saying is correct. But the answer is no. Not closed. Now, what do you think? Is C1 union C2 connected? Is C1 union C2 connected in our example? See, if you just think by one, like very, I should say, in a simplistic way, then it should be that, this cannot happen maybe. Right? I mean, two things are disjoint, then how can the union be connected, right? But see, connectedness is not about disjoint. Connectedness is whether they are disjoint analytically, meaning that can you do your analysis in one piece and not borrow anything from the other one. Okay, that's why in the definition of connected individual, we don't just say write it is a union of two disjoint sets. No, that's meaningless. You can do anything. You can write any set like that. But we say union of two disjoint open sets, right? So that's why it can happen that C1 intersection C2 is disjoint, but if they're like kissing each other, things like that, then the union is kind of getting connected. But let's see. So now let's think about this. Is this connected in our example? So it's a fine point. Use both the definitions and your intuition and think. Okay, if I ask you guys for just, let's say, for an MCQ, yes or no, what would you say for this example? I'm not asking general. For this example, after that we have seen that C2 is not closed. And similarly, though it follows from some theorems also, you can say that C1 is not open. C1 is not open in the bigger space also, but that is not what we are thinking now. C1 is not open in C1 union C2. Why? Yeah, you can also think about this first. So this is one question. I think you should think about this first, and then actually I had not prepared for this. I was basically I was going to ask as last time, C1 unit C1 and C2 are connected, and C1 intersection C2 is not empty. Then what can you say about C1 unit C2? But I think this is the thing that we learned today. I think I can say it as I learned new. Let's think about this. Okay, is C1 C1 is not open and C1? Can you show this? So what I'm saying is that, what does it mean to be open? Open means that any point inside you can make a ball which is completely inside. Yeah, because when you make a ball, it goes, and that's just the very definition. I mean, that it is closed. So you can see that it's kind of like if something is open, its complement is closed. You kind of already can feel that a little bit, right? Though we will prove that later. We don't need that now, so I'm not arbitrarily proving some property, because that is one approach in which you can do things. But you see, but just to make it very clear, okay, at this point, so I'm just going to mark. Let me do it with the white paint, white. Okay, at this point where I'm just making a whiteness. Okay, now just make it pink. Maybe it's not very clear. At the boundary here, here it is open, right? Because there, if you make a ball, you are only going to look at the part of the ball which is inside C1 union C2. That pink ball is in R2, but that is not what we're interested in. We will be interested in the red part of the pink ball. This is the ball in the union, and but that is completely inside in the union C1 union C2. So the portion there is not a problem. The portion is where these two things are tangent, is where the problem is, this yellow region, which is where the other part was also a problem, right? So it is not open. Okay, if it was open, then the job would have been done, right? Because C2 is open and this would be open. You write it as disjoint union of two open sets. But now it looks like you cannot write it. Okay, so I'll just go ahead and say this. Looks like C1 union C2 is connected. But we have not proved it. We have just checked one way to one obvious, or rather not just obvious, one canonical way to break C1 union C2 does not work. But is there any other way to break C1 and C2 and C2? So let's write the observation. The natural way to break C1 union C2, which is the first choice that we would have thought, natural way to break C1 union C2 does not work. But is there any other way? We have to show there is no way, right? Or if you can find some other way to show that it is connected, it's perfectly fine. That will be also perfect. In fact, the last class that was I was trying to emphasize, and today also I was planning maybe the next time, the ways to show connectedness, right? Because the way the definition is built, um, it's hard to show things are connected using it, right? It's mostly you took away contradiction and so on. But we had shown other techniques like path connectedness. So you can think in those terms also. Between any 2 points of C1 and C2, can you make a path? That's also good enough. Basically, that is what we will be using in complex analysis. This notion of connectedness is just topological, but to prove other things before using that version, we'll do that. Is there any other way to break up? Is there any other way to, one second, to break, just saying break up, okay, to disconnect, to break up C1 union C2? Yeah, is it possible? No, right? It looks like it is not possible. Because it's very clear, right? If there is any other way to break it up, then that will end up breaking up one of C1 or C2. Just think, right? I mean, if there is some other way to break up, it means that, 1 minute, has someone joined or? Oh, okay. Yeah. Right. So I was saying that no, right? No, there is no other way to break up. And that's just very obvious, right? If there is some other way to break up, which then it will break up C1, right? Or it will break up C2. This way in which we were breaking it up, it was not breaking up either C1 or C2, right? It was just trying to break up the union. It did not work. Any other way will actually break up C1 into two pieces, two actual pieces. But you cannot do that, right? C1 cannot be broken, C2 cannot be broken. They are obviously connected. So the answer is no. Please write a proof. Okay. Please write a proof. I have said if the argument is not clear, please ask. Otherwise, please write this and maybe you can try to write it and show also. Okay, that should be good. Please write it. Because this is not it was not an obvious fact to begin with. Is the argument clear to everyone why there is no other way to break up C1 union C2? Raghav and Rishabh, both of you, is it clear? Okay, good. Yes, please write the proof. Okay, because that is the way to learn. Okay, so you see, connectedness is about not just breaking up, but breaking up into two disjoint, not just disjoint, I mean, into two disjoint open sets. Okay, and obviously you can see that between any 2 points, there is also a path. If you take this point and this point, there is a path, right? And that path really does not miss anything because, the limit point is here and the other things are here. So it's connected. So yeah, so this is a very strange fact maybe, but it is true. Okay, C1 intersection C2 might be disjoint and C1 C2 connected, and C1 union C2 might still be connected if they are kind of kissing each other, tangent to each other, and so on. Okay. So let me not ask more abstract questions on this. Will not be very useful right now. Let's come to the next question which you are interested in. And that is, yes, actually, that's not a bad term, right? So analytically, they are kind of intersecting. You're right. Yeah, that's right. Because their closures are intersecting. That's right. I was actually going to ask that ask a question that will say that this is the only counterexample, in the sense that the union is connected if and only if they are pseudo intersecting, meaning that the limit points of one is some limit point of one of them is contained in the other. Otherwise, what you were saying initially that this is not possible was correct. It is not possible. These are the only situations where it's pseudo intersecting. Okay. But let's come to the actual question, which is of great importance for us, because we'll have sequence of closed sets and we'll have to kind of patch them up to make a global closed set or something. So that is In fact, this one will be useful. So let me just say property. Oh, no, I already said all this. So let's just ask the question. Okay. So C1 and C2 are connected. Now that was all counter examples and such, but now we are actually doing a problem. Okay, actually doing a, we'll have to prove something. C1 and C2 are connected in R2. C1 intersection C2 is not empty. Okay, C1 intersection C2 is not empty. Prove that C1 union C2 is connected. Now this is also a result that believable. This is a believable result. How do we prove it? Right. Exactly right. So the way we ended the last proof is how we are kind of going to prove this. But the problem is that the sets can be very weird and so on. So we have to prove it. And obviously last time we showed that the intersection need not be connected. You can just draw some easy pictures and see that intersection is non-empty, but it need not be connected. Need not be, it can be, like in this case it is. But we are just interested in the union now. So all this will finally help us to understand the difference between connectivity and path connectivity. We're trying to understand the difference between those two concepts, and to what extent can answer questions about connectivity be answered by the more concrete and concept of path connectivity. So after knowing, understanding these things, we can, yes, easily expressible. And usually the way the sets are defined, they are defined as a graph of a function or zero set of the roots of some from two variable function, so it's very amenable definition. It allows us to, in that language in which the phase set is defined, it's usually a better, easier way to prove connectivity. Okay, so right, but the problem is that path connected does not imply connected, and that's what we'll see once after we have understood these things, understood connected sets better by understanding the behaviors when intersection and union happen. But then we will later show that in our case of complex analysis, connectedness and path connectedness are basically the same. And that will be the upshot. And then we can go and do our complex analysis. Yeah, but let's do this. This is a simpler thing. This will be the last thing we'll do today. But I'm just ending a little time. So you see, the only way we can prove these things is by contradiction, right? Assume it is not, because definition of connectedness is cannot be written. There's no way to prove things, right? So you have to assume it is not connected and then proceed, right? Assume C1 union C2 is not connected. Now, what does that mean? It means that you can break it up a union of two open sets. Now it is just like the previous one. It will end up breaking up one of C1 and C2 because of the intersection being non-empty. So remember here, while you guys think, O1 and O2 are open in C1 union. C1 union C2 is the universe, is the mother space. They may not be open in R2 or whatever. So think about this. Let's discuss. Okay. So basically the idea is to use this to show that it will break up, right? One of C1 or so. So maybe it can be like O1 completely contains, right? I mean, in the sense, maybe I should, yeah, but just intuitively, I'm drawing a bigger one. Okay, you can draw a bigger one. There is some, but yeah, the point is that you're doing this, but you see, O2 it is disjoint, right? It means that O2 will be like this, somewhat like this, right? But then you see, it's breaking up C2. If you call this one C1 and this one C2, then you see O1 union O2 is kind of breaking up C2 in a non-trivial way, right? So to make this formal, we'll have to just say that O1, see, O1 contains C1 if this happens. One second. If yeah, okay. If O1 does not contain C1, if O1 does not contain, let's say C2 according to the picture, right? If O1 does not contain C2, then what does it mean? It means that O2 intersection C2, you take O2, you take its intersection with C2, and then you take O1 and you take its intersection with C2, is a breakup of C2. What do I mean? I mean that it is a breakup non-trivial breakup. Okay, so there are two things you have to show. So first thing is that O2 intersection C2 is not disjoint, and O1 intersection C2 is also, O1 intersection C2 is also non-empty, right? So is this true? If it's not true, then we will take some other case, right? What do you guys think? This is just set theory. Yeah, just set theoretically. What do you think? Is this correct? If O2 is something that does not completely contain C2, right? Can O2 be disjoint? If O2 is disjoint from C2, if O2 is disjoint from C2, then what does it mean? It means that O2 is contained in C1. Strictly contained in C. They can just say, yeah, strictly contained in C1. Is that right? Just said theoretically, right? O2 is strictly contained in C1 because C1 intersection C2 is not disjoint. But in that case, again, you can similarly get a breakup of C1, right? That will imply that O2 intersection C1 and O1 intersection C1 is a breakup. So this will be non-empty. If O2 is strictly contained in C1, then there will be some part of O1 also which is there in C1. Otherwise, how will you cover C1? So that way will be done. And if that does not happen, then this is non-empty. And this is obviously non-empty. O1 is obviously intersection C2. Otherwise, how will you cover C2? Okay. So you can see we are using both disjoint. We are using both non-disjointness of C1 and C2 as well. Okay. So they are not disjoint. We're using that basically. So it's a breakup that you can show. This is just a set theoretic thing. And openness is almost by the definition, right? If O1 is, this you can also easily show, but it's just by definition. O1 is open in C1 union C2, then O1 intersection C2 is open in C2. I mean, you can just take this as a definition of what it means for something to be open in a smaller space, right? It's intersection of something open in a bigger space. But in your case, you can also prove. You can just take a point and try to prove it. Okay, so we have an open breakup, and it's obviously disjoint because O1 and O1 and O2 are disjoint, right? So this covers C2. I mean, it's a breakup of C2, not O1 union, not C1 union C2. This covers C2. They are disjoint, and it's open cover. Both are open, and so that's what it means. We have ended up showing that C2 is disconnected, but that is a contradiction. Okay. Any questions? Please ask. Okay, no questions. Okay, so then we'll end the class, but I will just give some problems for you to try. These are connected with what we have done today and also form a bridge with what we'll do a little bit, not much, because this is not too much important in complex numbers, but it's very important in other places and to develop more intuition. Okay, so let Q be in R. Okay, is Q open in R? So don't answer this question now. Just think about them, write them clearly whenever you're answering them. Is Q closed in R? Is Q union pi open or closed in R? Okay. And obviously, next questions are, is Q connected in R? Okay, find if not, and just find a subset. If the answer to this is yes, then you already have the answer to the next question. This is what I'm thinking. If find a subset, because this is one of the examples, one of the things that has struck me really, and also stuck with me when I was studying connectedness, even later also. Yeah. So find a subset. Find a subset of. There is a joke that I ended up, unknowingly say somewhere. Uh, it made total sense, but I'll not say that because then the answer to all this will be given, maybe. But still, you have to do it. But let's not. Let's just try this. Find a subset of Q which is connected. Obviously, don't just give me points. Now, don't just give me, say, just a number. Some good subsets. I mean, more than one thing. Find a subset of Q which is connected. This will help us to. Yes, right. The single points, yeah, they're obviously connected by definition, but yeah, not very interesting. This will help us to answer a lot of interesting, because connectedness is also connected with the way we define dimension of spaces and so on. So we'll explore that also, but not little later. Yeah. So note this down and give yourselves a few minutes. If you have any questions, you can ask related to what we've done today. Otherwise, we'll end. So I'll just wait a few minutes, and then I'll end the meeting. See if you have any questions. Okay, so if there are no questions, then I'll just, yeah, I'm still here, so you can ask me if you have any questions. Okay. Okay, then. So please try this. We will shortly do this again next Saturday. Okay. But yeah, I'll announce one day before also. Yeah. Okay, then.